Greetings, mathematicians. We are going to continue 4-7 scale change and trigonometric functions. So first off, let's look at what the frequency of sine wave is. So in example 4, which uses this graph here, notice that the parent function cosine of x completes a certain number of cycles for every one that the image does. So let's just count it off. If this is a complete cycle from here to here for the image, let's see what the parent does. It goes here and 1, 2, and 3. So in the end, we see that in example 4, it completes 3 cycles for every 1 cycle that the image completes. So we say that y equals cosine of x, the parent function, has 3 times the frequency. And frequency usually is about time, how many times something happens in a second the in a minute. So in general, the frequency of the periodic function is the reciprocal of the period. So let's look at example 5 here, but before we do that, let's get a little bit of background about tuning forks and sound. Usually, when we graph the sine wave of something like a tuning fork, time is going to be the x-axis, and pressure, how much pressure we apply, is going to be on the y-axis there. So of course, more pressure means more sound, so the amplitude will get higher, and certain frequencies will have the same period for its wave, no matter what. So one tuning fork will always have the same wave in terms of frequency, but it might have a higher amplitude based on pressure applied. So a tuning fork vibrates with a frequency of 512 cycles per second. The intensity of the tone, so intensity, we could actually think of intensity as looking forward to amplitude of the tone, is the result of a vibration whose maximum pressure is 22 newtons per square meter. Find an equation to model the sound produced by the tuning fork. So one thing that's a given is that this will be a sine function. And it's going to be in this form. Again, B is my amplitude and A is my period. So by the definition of period, previously we saw that the period is equal to 2 times pi times the absolute value of A. And A is pretty much the scale of the parent function's period. So the parent function period is 2 pi. So this is how it's being scaled. So ultimately, we're looking for that A right there, what percentage or how the parent function is scaled. Okay, now we know that frequency is the reciprocal. So it's going to look like this. And now, using the information from the word problem, I'm going to substitute 512 in there to get 1 over 2 pi times the absolute value of A. Now we're just going to quick do Jimmy Jig. This here replaces with this, kind of like Freaky Friday. So absolute value of A is equal to 1 over 2 times pi times 512. And now let's finish it up. That's going to give me A is going to be a positive or a negative 1 over 1024 pi. So that's what A is. Now, we know that this fraction is going to go into the denominator here. So placing it in the denominator means I'm going to multiply by the reciprocal. And the other part is very straightforward. This is my amplitude right here. So that's my B. So I'm just going to substitute in y equals 22 times the sine of 1024 pi times x. If you need to see where that came from right here, I'll just show that real quick. So x over 1 over 1024 pi. So that now means x over So we have to, dividing by a fraction. Dividing by a fraction is the same as multiplying by the reciprocal. So x times 1024 pi. Okay, so that is my result right here. Now, your job is to attack, kill, destroy this one and see what function you get. The result should be y equals 15 times the sine of 880 pi times x. On the last page and last example is we are going to, without technology, we're going to determine how many solutions each equation below is on the interval of one complete cycle of the parent function. So between 0 and 2 pi. We're going to confirm our answer with a graph. Now, fundamentally, let's recall in algebra what's true. If I gave you this equation that 2x equals 12, then most of us would do the inverse and divide, okay? But it turns out that graphically, this can be represented as a function, and this can be represented as a function. So if I pull up Desmos here, and I see what we have, 2x equals 12, it yields me 6, just like I did algebraically. But let's look at this graphically, what will happen. If I select the 2x, it graphs this function here, and y equals 12. Oh, I can't see it, so I need to change my window there. Okay, now ultimately what we're doing is we are looking for the intersection. Essentially, I've created a system of equations, and our goal is to find the intersection of those. So when I select the intersection, notice what I get. Oh, look, x is 6. X is 6. Well, what's y? Y is the output right there. Y is 12 already. So we know that essentially each half can be represented as a function, and we're just trying to see where those two intersect. So let's do that here. So I am going to graph this function here, and I'm going to graph this function here on this. Now, in order for me to attack this one, I must see how it is transformed based from my parent function, which is the cosine of x. So the first thing I'm going to do is graph the parent function of cosine x. Now, before I attack that, I want to decide what my units are going to be. Where am I going to put my 90 degrees or my pi over 2? Do I put pi over 2 here? Do I put pi over 2 in the second one? What am I going to do? Do I put pi over 2 here? Or should I move it over and put pi over 2 here? So where is this going to happen? Now, this decision that I'm going to make actually is going to affect quite a bit. So notice that first off, I recognize that this function right here is a compression by 3, excuse me. So it is a horizontal compression by 1/3. So I just cut everything into 1/3. So this actual 1/3 is extremely helpful because if I put my pi over 2 here, and when I squash by 1/3, it's somewhere in this vague territory. Same thing here. If I place my pi over 2 here, then it's going to be somewhere over here in my vague territory. So pi over 2 being squashed from here actually brings me to a nice place there. So that helps me make my decision about where pi over 2 will be. So here's pi over 2 and pi, 3 pi over 2, and lastly, 2 pi. Now, my parent function is cosine, so I start high. Now let me go ahead and place units on this. I'm going to count by 1/3 there, so that's my 1 and my -1. And here, I'm going to start high, go through that, low, x-intercept, and high. So let me go ahead and graph that real quick. Try to make your curves going in for a nice gentle landing before I take off again, like so. Now the reason why I'm just dashing this or drawing it lightly is because I don't want this to be in the way because I haven't done my transformation yet. In this case, I'm going to compress everything. So notice this point here can't be compressed. It already stays as is. So let me just plot that point. This point is going to get translated, excuse me, not translated, but compressed to there, a third of the way there. This is going to go a third of the way to here. So that means this trough is going to go to there. Now continuing, the x-intercept here, 1/3 of that goes to here. And then to complete the cycle, my crest here compresses to this here. So now all I have to do, and if I were to graph this, come in for a gentle landing, and back up. Oh, that one's ugly. Fix it. There. Now, of course, I'm just going to repeat that pattern because it asks me to go all the way to 2 pi. So I'm going to place points here, points here, points here, points here, and then just keep going, following that pattern. Keep going, and done. No, I'm not done, just tricking. So number 2, what did I do? I graphed anything that happens, my scale change, my image. Okay, now what I have to do is graph the right side and check for the intersections. Okay, so what's my right side is 0.8. So halfway is here. So 0.75 has to be somewhere about there. So I'll pick another color here, and 0.8 somewhere about there, 0.8. So let me get my line in there, and it's just to there. And of course, ultimately, we're trying to figure out where things intersect. So here's an intersection, which is roughly pi over 2, 12. So pi over 12. Here's another intersection right there, which is roughly 7 pi over 12. And of course, this one here, and this one here, and this one here, etc. And as we see, they're just going to be multiples of that by adding, in this case, I'm going to add a whole cycle to that and a whole cycle to that one there. Now, of course, it's wise for us to return to the question, without technology, determine how many. So not the actual solutions here, just count the number. 1, 2, 3, 4, 5, 6. So in this interval, there are 6 solutions. Now you're going to repeat that same process here, but note what happens with the amplitude here. Things get shot up significantly. So if my original tangent function looks like this, things are going to get stretched out like that by 5. On top of that, it's going to be stretched horizontally by 2. So make sure you attack in that way. All right, I hope you enjoyed this wonderful lesson of trigonometric functions. Have a good one.